All right, welcome to General Relativity and Geometric Algebra, episode 5. And this is going to be our first example video where we deal with polar coordinates and then derive all of the like the coordinate basis vectors, the um, connection bivectors, and then all of the curvature tensors or curvature multivectors. So before we begin, we'll be using this convention. So we'll use c equals 1. So the speed of light is equal to 1 in this. So we're using natural units. So then the space-time vector, or space-time position, vector is the following. X equals t gamma naught. So that's the time-like direction. Then you have the distance in the x direction, and then the distance in the y direction, or position rather, the position in the xy, and then z direction. In polar coordinates, which is what we want to get this into, in polar coordinates, we have that Rx is equal to R, which is the total length or total position, or it'd be the total, what do you call it? Spatial length. That's the word. Sine theta, cosine phi, Ry is equal to R sine theta, sine phi, and Rz is equal to R cosine theta. And this is all where R is spatial length, or rather, I can just say magnitude. And theta is the polar angle. And phi is the azimuthal angle. Okay, so now we want to express the position vector in polar coordinates. And we're going to use that to create the coordinate basis. So we have x equal, oh, it's the wrong color. We have x equal to t gamma naught plus r sine theta. And then we have cosine phi gamma 1 plus sine phi gamma 2 plus r cosine theta gamma 3. Okay, and we'll now choose, or so say, thus. So we'll now choose new indices. So new indices, I'm going to label them alpha, and it goes through t, r, theta, and phi, all of our variables. They correspond, each one of these corresponds with one of our variables. We have time, uh, time, position, and then, or I guess rather magnitude, and then the orientation space is given, 3D space is given by these. Okay, so we have that. These are the coordinate indices. So for the coordinate basis G alpha, then we can find GT as being the derivative with respect to time of the position vector, and we just get gamma naught. And same thing for GR, we take the derivative with respect to R of X, and we get sine theta cosine phi gamma 1 plus sine phi gamma 2 plus cosine theta gamma 3. And similarly, we have g theta, which is going to be the derivative with respect to theta of x, and that will give us r uh, cosine theta cosine phi. I'm just going to copy and paste this. Then minus r sine theta gamma 3. And lastly, we have g phi, and this is just the derivative with respect to phi of x, and we get r sine theta minus sine phi gamma 1 plus cosine phi gamma 2. And so these are the coordinate basis vectors. They and to find, or what we need to do now is find the reciprocal basis vectors so that we can compute the coordinate metric tensors. Or actually, I got that backward. We're going to find the metric tensor for this, or using these, and then use that to build the reciprocal coordinate basis. So the reciprocal coordinate basis satisfies the following, and that's G alpha dotted with G beta is equal to alpha beta. And this is the same as saying that G alpha beta, the metric, times the reciprocal coordinate basis, and then summed over beta gives you G alpha. And then if G alpha beta is diagonal, so this is saying it's diagonal because all the beta terms go to 0 except for the ones that are equal to alpha. Then you have G alpha equal to 1 over G alpha alpha G alpha. So this is a scalar, so that means that now we can compute the reciprocal basis using the metric and the standard or the normal coordinate basis. And the reason I assumed, or why I stated this property in the case that it's diagonal, is because this we'll see is diagonal. And that diagonality just means that the vectors are perpendicular or orthogonal to one another. This is orthogonal to all of these, and if you go through and prove it, you'll see that all of these are orthogonal to each other. Actually, I recommend that as an exercise. Okay, so best to compute, it's best to compute G superscript alpha after computing G, or the metric. So therefore, compute the metric, and it is given, or and I'll make it a little bit bigger. Here we have gamma naught dotted with gamma naught. That's just going to give us 1 for the first term. So we have 1. But then gamma naught dotted with gamma 1, gamma 2, gamma 3 is going to always be 0. And so we get 0, 0, 0, 0, 0, 0 in these terms. And then here, when we take the inner product, this is going to go to 1 because you'll end up with cosine squared plus sine squared, and then you have a -1 out front because these square to -1. So in this, you'll end up with, yeah, and then you'll end up with a sine squared. So you'll end up with minus sine squared minus cosine squared. And so you get that this is squareston -1. -1, and then for similar reasons, it'll be 0. And this one should behave almost exactly the same as this, because even if I flip having a cosine and sine, they behave the same way when you square them. The only difference is now that there's this factor of r. So we get minus r squared. And then for this last term, this is just going to give us -1 again. And then this is going to just be squared, and this will be squared too. So we'll end up with r squared sine theta squared. So r squared sine squared theta. And so that is the metric. It is built from all the inner products. Okay. So therefore, we're going to compute the reciprocal vectors using this right here. So gamma t is equal to 1 over, and then this value, so 1 over 1 gt, and that's just going to be gamma naught. Gr is going to be 1 over -1, 1 over -1 gr. And so in this one, you get minus sign, then front. Then g theta is going to be 1 over minus r squared g theta, which is going to cancel these r's, and then you're going to end up with just 1 over r. One over r, 1 over r. And lastly, you have g phi, and that's going to be 1 over minus r squared sine squared theta, right? Because that's this term. And then g phi. And that will end up with a term like so. So minus, I forgot to put in front of these, minus and plus. And then we'll end up with the same uh, minus sine phi gamma 1 plus cosine phi gamma 2. So that's the reciprocal coordinate basis from the computed using both the original basis and the metric. So what's then the metric using this? And this implies that G alpha beta corresponds to, we have 1, 0, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, 0. And then we're going to have minus 1 over r squared, and then minus 1 over r squared sine squared theta, like so. Right, and now we're going to compute tetrads from this. So let's recall the relationship to tetrads. The relationships to tetrads are E alpha m G alpha equals gamma bar m. And notice that for tetrads, I'm now putting a bar underneath to just distinguish them from their traditional um, basis counterparts. And then I'm putting a bar underneath these terms here to distinguish so that you have when alpha and m are like this, there's a bar, and you'll see that it's not the same as alpha m when I go without a bar. And that's because when I put indices here and here, here and here, it's hard to distinguish unless I have a bar. And okay, so we have this relation, and then the other relation is em alpha g alpha equals gamma bar m. These are the tetrads. And the things that bring the coordinate bases to the tetrads, these are the Vierbein, which is German for four-legged, but I think it technically means four bones. So the thing is that um, the Vierbein, spelled it wrong, Vierbein are effectively the positive square roots of the metric. And specifically, this is E bar alpha. This is like the square root of this metric. And this right here is like the square root for this metric. And so it's easy to compute. And the reason that these are like this is associated actually with the superscript, not the lower script, is because this and this, these are inverses of each other. And so you can think about taking the square root of the inverse, or the square root of the inverse, and then multiplying that times the, what do you call it? The other basis to go into a tetrad. And so if this essentially, this G alpha is equal, G alpha is equal to E to the alpha M like this. And so when you multiply by this, you're canceling out this factor. And likewise here. And you end up with the following. So E bar alpha M you end up with what's the square root of 1? It's just 1. So square root of -1, but the positive square root is just 1 again. And then positive square root of -1 over r squared is going to just be 1 over r. And the positive square root of 1 over r squared sine, or sine squared theta is just 1 over r sine theta. And then here it's just the reciprocal, like so. So then these are the coefficients that you use to bring each coordinate basis to a tetrad. So let's now compute the tetrad. So therefore, gamma naught, gamma bar naught is equal to just GT, which is just the traditional gamma naught. Because the coefficient, recall, this is just 1. So we have gamma naught 1 times GT. And for gamma bar 1, we have again 1 times our GR. So we get GR, and GR is just the same as this right here. And then G2 is just going to be 1 over R G theta. So let's copy G theta. And every factor of G theta has R in it. So this 1 over R cancels it. And then for gamma bar 3 in the tetrad, we have 1 over R sine theta, G phi. That gives us this. So this is the tetrad, or what do you call it? This is the tetrad that you can construct using this Vierbein and then the coordinate basis. So I encourage you for the next, or because in the next video, I'll be using the reciprocal basis or the reciprocal tetrad. And so I encourage you as an exercise to compute gamma bar naught, gamma bar 1, gamma bar 2, and gamma bar 3. It's the exact same procedure that we used to get this. So I encourage you to calculate that. And then if you also want, prove that m that the inner product of these tetrads just returns the Minkowski metric. So this is again pretty easy to prove. You just all you have to do is just carry out the dot products between all of these vectors. But yeah, that covers this part, and then I'll record part 2 later.